Alrighty, here we go, our last unit for the semester. And in this lesson, we are going to learn about differential equations. And really, differential equations is kind of the big overarching thing of all of these things. So we're gonna do differential equations. What are they? What does it mean to have a solution to them? How do we actually solve them? We'll look at slope fields and how they're related to differential equations. What can you use them for? And then we're going to look at something called Euler's method. It looks like Euler, but you pronounce it Euler. So we're going to do Euler's method, and it's a numerical approach to solving differential equations, but we'll learn all about that. So this is our kind of table of contents for today. So let's get into the meat and potatoes of it. Okay, so first I just got some definitions for you. So first of all, we're talking about differential equations. What the heck are they? Well, they're equations with a derivative. That's it. That's all there is to it. So here we have a equation because there's an equal sign. There's a derivative over here. Boom, we got a differential equation. So you've been dealing with differential equations and you didn't even know it. This is a pretty simple one. This is called a first order differential equation because we have a first derivative. If our highest derivative was a third derivative, we would have a third order differential equation. In this class, we're only going to be solving first order. We're going to keep things pretty simple, but kind of building the foundation for what you can do later. What does it mean to be a solution to a differential equation? Well, a solution to a differential equation, you can actually have a general solution or a particular solution. As far as a general solution goes, it is the set of functions that have a derivative equivalent to the given differential equation. So for instance, this right here, y equals x squared plus c, because of this c, this actually represents a bunch of different a bunch of different equations. In fact, it's an infinite number because c can be any arbitrary constant. So this isn't just one function, this is a set of functions, and these functions all have the same differential equation. So this is a general solution to this differential equation. A particular solution just means we're given something to find c. And so, and we call that the initial condition. So for instance, if I said that we also know that y of 0 equals 2, when x is 0, y is 2, if you let x equal 0 and y equals 2, that will give us c equals 2. So this represents now the particular solution to this differential equation, given this solution. So there's one particular solution. So there's some general vocabulary to get us started. And then a strategy that we can use to solve differential equations is called a separation of variables. And as long as you can write your differential equation in this form, you can use separation of variables. It's the easiest technique to use to solve differential equations. That's going to be the technique that we do in this class this year. So if you can say the derivative is a function of x times a function of y, you'll be able to do separation of variables. So we have examples of it coming up, but just to show you what this means, for instance, if we take this differential equation right here, dy dx equals x over y. Well, right now it says x over y, but I can write it in an equivalent form where it's a function of x times a function of y. And so that means that we'll be able to solve this using separation of variables. So there's that. Now, we're not actually going to solve this particular one. We'll look at others, but let's go ahead and actually examine this idea of what's it mean to be a solution again. Here, we have an example of a second order differential equation because we have a second derivative in it. And I know I said we weren't going to be solving these. We're not. But how do you check a solution? And so we're supposed to determine whether the given function is a solution to the differential equation. So this right here, this, in order to check it, to check a solution, how you always substitute back into the equation. So this equation, though, has a second derivative and the function. So we take the function, find the first derivative, so we can find the second derivative. and then we will plug in the second derivative in for the second derivative. We'll plug the original function into the original function. In this case, we did not get something that was true, so y equals sine x is not a solution. That's all it means. So if we were to check out, see if I can make this a little smaller so we can see it. If we wanted to check out this one, and just by the way, like this has no c, so this was would have been a particular solution. This one has a value of c again. There's no plus c, so that means we found the value of c. This is called the general solution because c is still there. Anyway, let's check this one out. So we find the first derivative and the second derivative, and then we're going to plug this into the second derivative, the original function into the original equation, and lo and behold, we do get 0 equals 0. So yes, this is a solution. And if we did the same thing for this guy right here, this is the first derivative, this is the second derivative, plug them into the second derivative in the original function, and we do also get a true statement, an identity. So this is also a solution. So there you go. Okay, let's actually solve them. Let's go back to that one that I did above. So we had dy dx. We knew this was something that we could write as a function of x times a function of y. So we can do a separation of variables. So how does that work? Okay, so here's the original function. I want to get all the y's on one side, so I'm going to move this y over here. And I want to get all the x's on the other side, so I'm going to move this dx over here. And I'm going to do that by multiplying both sides by y dx. This way the y's will cancel, so I have x dx on the right. The dx's cancel, so I have y dy on the left. I have now separated my variables. Once you've separated your variables, you can integrate. And so we integrate both sides. And remember, when you integrate, we will have a plus c. So we have a plus c on one side and a plus c on the other. And these are different, or actually I should say they could be different arbitrary constants. So that's why I put a little subscript of a 1 and a 2 here to show that, yeah, this is a c and this is a c, but they're different c's. However, I can always combine them together into another arbitrary constant. If I subtract c1 from the left and the right, that'll cancel these out. And an arbitrary constant minus an arbitrary constant is just another arbitrary constant. And so what we usually do, this will be the only time you see me do this, where I put the c on plus c on both sides after I integrate. Because we can always do this. We'll always get a plus c on both sides. I can always subtract one of them from both sides to put plus c just on one side. We just always, when we're solving these, we'll just put the plus c on one side and kind of skip these steps right here. But anyway, once I do that, then the idea is let's try to get the y by itself. So I will multiply both sides by 2. And again, remember, c times an arbitrary constant is another arbitrary constant. And then I'll take the square root of both sides and boom. And notice the c is inside the square root. So when you're solving differential equations, your equation will often not end with a plus c. Even if you're finding a general solution, that plus c might end up kind of moving somewhere else into the equation. In this case, it moved underneath the square root. And there you go. There's solving by separation of variables. In case you're wondering why here I didn't make this a C3 to show that when I do 2 times C3, I get yet another arbitrary constant. You're right, I should have. Oftentimes, when we're doing differential equations, you'll see people get a little sloppy like this and not use subscripts at all throughout it. I really should have, and but I did do it partly because I wanted to show you that this is oftentimes the subscripts are dropped. But you really should be keeping that in mind. this is a different arbitrary constant from that one, which is different from this one, which is different from this one. We have four different arbitrary constants here. Okay, so there's our first example. Let's take a look at a couple examples here. I want you to go ahead and try these on your own. Again, separate the variables. This one's a little easier to separate the variables, a little more straightforward. I am giving you something you can plug in at the end to find the value of C. So try example 1. If you want a challenge though, go ahead and try example 2 also without looking at the solution. But if you do scroll, if you're looking at the notes that are posted online, if you do scroll, you can find these solutions later. But pause the video right now before we take a look at them here. Okay, let's take a look. So here's the first one. Pretty straightforward as far as separation of variables, because all I need to do is move this dx over to the other side by multiplying both sides by dx. So wind up over here, integrate both sides, and in order to integrate the right-hand side, we're first going to rewrite it. We're going to divide each one of these terms on the top by the square root of x. Excuse me. And then we'll integrate, and we have the plus c. And notice I put the plus c on one side of the equation. So there's our general solution. Okay, let's find the particular solution when we let x equal 1 and y equal 2. So here was the our general solution that we found. We're going to let x equal 1 and y equal 2. And when we do, and we go through all these steps, we find that c is 14/15, and so there's our particular solution. So let's take a look at those. Just kind of chew on them, see if you have any questions. Now, the other thing too that I want you to take a look at is over here in the yellow cloud. Just as a little side note, the dx and the dy have to always either go in the numerator or be multiplied next to the fraction or the integrand. And it means the same thing. So like, why didn't I just move this over here and the dy over there besides that's more steps? It's because the dx can't be in the denominator when I integrate. I had to move this over to the right-hand side. If your dx or dy is in the denominator, that means this, and this is gibberish. 1 over dx in an integral, gibberish. You cannot integrate this. And so it has to be written that so that the dx or dy is either in the numerator or multiplied next to it. So just food for thought. All right. Here's the second one. So as far as separation of variables goes, if I go ahead and I'll isolate, sometimes when it's a little harder to see, first of all, we'll write the y prime as dy dx. But if it's a little harder to see how you're going to separate the variables, you can try solving for dy dx. Because if separation of variables is going to work, that will often help. And now we can see I'll multiply both sides by dx to get the dx over here, and also in the right place, not in the denominator. And then I want to get rid of this y, so I'm going to divide both sides by y to get down here. Now, as far as this negative goes, the negative really could have gone on either side. In general, because we are going to eventually solve for y, it's easier if we leave the negative over on the right-hand side and only move the y. Try to keep the y as isolated as you can. That's just kind of a general rule of thumb, just because it usually helps to solve for y later. Okay, so I'm going to integrate both sides, and I do get natural logs in this case. And again, here's that C1, C2. We don't have to do that. See how they do end up getting combined into this C3. Don't forget we got these absolute values on there as well. Now I can, to get rid of the natural log, I can raise both sides to the power of e, or make them both exponents to the e, I should say. You can't just drop the natural logs because the c does not have a natural log. So we have to do something like this. That will drop the natural log on the left-hand side. And then over here, this is a little trick you'll get used to, because this often happens where we end up with logs and we have to do this thing with e. In your exponent, you have addition, and remember that means we can separate it into multiplying two factors with the same base. And I've just moved this exponent here to make it x to the negative 1. E to an arbitrary constant is another arbitrary constant. And then over here, my e and natural log can cancel, so I'm left with this. Now to get the y by itself, I'm going to go ahead and remove the absolute value and put a plus or minus on the other side. And the plus or minus is taking care of the absolute value here as well. I can drop that. And then plus or minus an arbitrary constant is another arbitrary constant. And so there's my answer right there. So pause the video if you need to take a look at that and kind of see what's going on. But there we go. All right. So maybe we can observe rates of change, but we can't actually find the equation for the derivative. So maybe through experiments or observation, we can record data with rates of change. So how can we use this to approximate a solution? And that's what slope field's for. And you can see right here, these are 3 different slope fields, and it's exactly what it sounds like. It's a field of slopes. Because remember, derivative slopes. Anyway, there's just a bunch of little line segments here, little mini line segments. Each one of these represents a different slope. And so let's actually take a look at this. Now, if you want to just try, I haven't really explained much, but if you want to try pausing the video and see if you can do this, go ahead. Let me explain a little bit. So we can see for part A, all these slopes right here down the y-axis, they all have a slope of 0. And any point on the y-axis has an x-coordinate of 0. So that means that when x is 0, it will make the slope equal 0. We can see over here, all these slopes are positive. In fact, if we actually pick a point, going by their scale, we can see that this is 1, here's 1. So at the point 1, 1, there is the slope right there. That slope kind of looks like it's definitely positive. It looks like it could be a positive 1. But at the point 1, 1, this represents the slope. At the point 2, 1, we can see the slope got a little steeper. Over here, where x is negative, we have negative slopes. And so that's what slope fields mean. So see if you can figure it out. Go ahead and take a look. Okay, let's do this together now. So this guy right here, the one that we were just looking at, so everywhere x is 0, the slope is 0. Everywhere x is 1, it kind of looks like the slope would be 1. Everywhere x is 2, looks like the slope is 2. Everywhere where x is negative 1/2, the slope is negative 1/2. It looks like the slope corresponds to the x-coordinate, which is exactly what's going on here. The derivative is x, or the slope is the x-coordinate. So this right here is A. And then likewise, look at 3. 3 says the slope is the y-coordinate. The slope is the y-coordinate. And that looks like what's happening right here in C. On the x-axis, we have a whole bunch of slopes of 0. That's where y is 0. When y is 1, looks like the slopes might be 1. When y is 2, looks like the slopes might be 2. When y is negative 1, the slopes are negative 1. So this is C. And then by process of elimination, we can see that this is B. And so how do we see that? Well, let's take a look. This is x plus y. So if we there's different ways you can do this. So one is just kind of like reasoning your way through it. If we let y equals 0, which means we're on the x-axis, the slope is the x-coordinate. Slope is -2, -3/2, -1, -1/2, 0, 1/2, 1, 3/2, 2. So that's matching. And then here on the, oops, I was on the wrong one though. Look at that. Need to be over here on B. And then if we look when x is 0, the slope is the y-coordinate. When x is 0, you're on the y-axis. Slope is 2, 3/2, 1, 1/2, 0, -1/2, -1, -3/2, -2. Again, it looks like it's matching. If you checked any point right here where x is 2 and y is 2, 2 plus 2 is 4. That's a very steep line. Looks like it could have a slope of 4, and so on and so on. Okay, so that's what slope fields are. And what we can often use slope fields for, I mean, sometimes it's just a nice way of representing. I mean, actually, let me go back up here. This represents a whole bunch of different solutions to a differential equation. So this is one way of representing a general solution because we have all the different functions here. And you may be going, what? Well, let's look down here. So here's the slope field. And if we were given this initial condition, we know that when x is 1, y is 1. So here's that point right here. You just kind of follow the flow of the slope field. Think of them almost like currents, and you're going to follow the current. So the slopes are starting off pretty negative, but as we go, it does look like they get less and less steep, and then they're not as steep here. But then see how the slopes over here on this side, they're all going positive. So we have to follow the current, but they're getting more steep as we go to the left. So we kind of follow the current and get more steep like that. And that's what a particular solution would look like. Now, the more detailed your slope field is, the easier it is to follow the current more accurately. But this is kind of the general idea of a slope field and how you can use it to find a particular solution. Now, if we want a more precise way of using a slope field to find a particular solution, that's what Euler's method is, and we'll be looking at that. But right now, just kind of think of it as following the current. So, yeah. Okay, so let's get an idea of what it's like to sketch a slope field. So let's say we have this, we're going to do two of them. Now, slope fields can get a big pain in the butt to do by hand. So we're not going to make a very detailed slope field. I'm going to show you two different ways of doing it. Let's look at this first one, where the slope is 2x plus 1. Whoops. So how can we do this? Well, one way is you can just make a table of values and find your slopes. So for instance, I'm just going to, like I said, we're not going to make a very detailed one because they are so tedious to do by hand. We're just going to do 9 points. 9 already is enough just to get the idea. So I'm going to do these particular 9 points. And so if I'm going to do those particular 9 points, then I will make a table of values. And we are literally just going to plug them in. 1, 2, 3, 4, 5, 7, 8. I believe that's 9. So starting at the top, this point is -1, 1, -1, 1. This point right here would be 0, 1. Then we have 1, 1. And then over here we have -1, 0, 0, 0, 1, 0. And then doing the points on the bottom line, we have -1, -1, 0, -1, 1, -1. And then all we have to do to find the slope is do 2 times the x-coordinate plus 1. So this time the slope won't depend on y, it's all about x. 2 times the x-coordinate plus 1. So 2 times -1 is -2. -2 plus 1 is -1. 2 times 0 plus 1 is 1. 2 times 1 is 2, plus 1 is 3. -1 times 2 is -2, plus 1 is -1. And actually you can see that -1, 0, 1, -1, 0, 1, -1, 0, 1. I'm just going to repeat because this only depends on x. My slope is just going to repeat. So I've kind of already calculated it. All right, now let's do our best to draw a slope field. So at the first point, we're going to draw a slope of -1. You just put a little dash that would have that slope. And then a slope of 0. Oops, I'm looking at the wrong thing. So a slope of -1, a slope of 1, a slope of 3. So a slope of -1, slope of 1, and a slope of 3. And then I just do it again. Slope of -1, slope of +1, and a slope of 3. -1, 1, 3. And there we go. That's the start of a slope field. So you can see, very tedious. Kind of a pain just to do 9 points. I have seen them on the AP, not very often, but I've seen it before. It might have been a practice test, I can't remember, but College Board does make that practice test, so I've seen them ask about drawing a slope field, but they've never asked for more than 9 points. All right, let's say you are going to do this one. We could do the same strategy, but something else you can do is called finding isoclines. So I just want to show you a different strategy. We're not really going to stress in this class too much drawing them. Honestly, these days, computers do it for us, so thank God for that. But it's always good to understand what the computer's doing under the hood. Remember, this is like dy dx is like slope. So anytime you hear iso in math, think same. Cline, like incline, same inclination, same slope. So let's say that we're going to find an isocline of 0. That means the slope is 0, and the slope is x plus y. So that means if I solve for y, everywhere along the line y equals -x, you have a slope of 0. So the line y equals -x is that diagonal line that goes down this way. So everywhere along those points, we have a slope of 0. And you see I'm finding a whole bunch of points right now with very little effort. We'll just do a couple more. We won't actually complete this, what do you call it, slope field, isocline of 1. So we're going to let the slope equal 1. 1 equals x plus y. If I solve for y, we get y equals x, nope, y equals -x plus 1. So everywhere along this line, we will have a slope of 1. So this line has a y-intercept of 1 and a slope of -1. So a y-intercept of 1, but a slope of -1. So these points all get a slope of 1. If we do an isocline of 2, 2 equals x plus y. So y equals -x plus 2. Now this gets a little harder to draw. I mean, once you get to slopes of 2, it's really hard to draw by hand. Slopes of 2, 3, 4, especially a little dash. But we know we're going to have a y-intercept of 2, so along this line. So these guys are going to look like this. And you just kind of keep this up. And then you can get, we could fill in the slope field relatively quickly and see it's getting a lot more detailed than just 9 points here. So that's another strategy for doing them. All right, let's get into the fun stuff though, Euler's method. So Euler's method. Euler's method produces a numerical approximation to the solution of a first-order differential equation given an initial value. That's a mouthful. Basically, I'm going to scroll up to some of our earlier work. Bear with me while I scroll. Hope you don't get a little seasick. Remember these guys right here? So we had this differential equation. Here was a particular solution to the differential equation. And then now that we have a particular solution, we can find when x equals one number, what does y equal? But we had to be able to solve this differential equation to get this general solution. And then we would have to be given a condition to be able to find the value of c, to find this particular solution. And then finally, we can use this particular solution to find any y given x. But that requires a lot of things. That requires that we are able to solve a differential equation and get the general solution. It also requires that we're given an initial condition to find this. There's a lot of things that have to line up. And so what if that all doesn't line up? What if one of those pieces is missing? Well, that's what we got Euler's method for. So we don't actually draw slope fields when we do Euler's method, but Euler's method is kind of using the idea of slope fields behind the scene. So here's what Euler's method is doing behind the scene. So we do have to be given an initial condition. So let's say that we're given this initial condition, and I want to know what y of 0 equals. So what I can do is I basically will follow this line until we get to another, this kind of looks like it's actually, might be parallel still. I'm going to keep following it, but now we're getting over here to where this line is going this way. Now I'm going to follow this slope here, and then it looks like the slope is shifted here like this, and now I have a y value. So it has, what Euler's method will do is it gives us a very specific algorithm to follow to tell us how to find the currents of the slope field so that we can use it to find another point on the curve. So here's a better picture of it right here. Given this initial value here, we'll follow the slope until we get here. And now we're going to follow this slope on the slope field until we get to the next step. And then we follow that slope until we get to the next step. And then we follow that slope until we get to the next step. And we can keep following this as long as we need to until we get to the y coordinate that we're looking for. Now we can see, like, if this lighter gray curve represented the exact solution, what tends to happen with Euler's method is the more steps you take, the further you're going to get away from the actual curve. And also the bigger the steps are, the further away you get from the curve. So we're going to take very small steps of x, and we're going to try not to take too many to get to where we need. So that's the idea. Now, before we actually do it, let's just get used to a little bit of notation. Just a new thing, it's no big deal. But we've been doing dy dx. We know d dx, and we know y prime. These are all notations for the derivative. When you're seeing Euler's method, because Euler's method is often dealing with differential equations in terms of x and y, a lot of times we'll be using this notation. So just when you're looking it up in books, not everybody uses this. Some people still go back and, use one of these notations, but this is just another notation for the derivative, the first derivative in terms of x and y. So where does Euler's method come from? It actually comes from the equation of a line. This is point slope of a line. If I solve for y, just add y1 onto both sides, I get this. This difference of x values is the same thing as delta x. And when we write Euler's method, the slope and delta x actually swap places. We usually write them in this order. Our delta x is, we're going to use h for that. I don't know why, it's kind of a standard. But what are your x's going to change by each time? That's h. It's called your step size. This delta x is this width right here. How much space between the next step to finding the slope of the next line. And then this is our notation for the derivative, slope derivative. And that's it. That's pretty much the equation. Euler's method is what's called an iterative process. You're going to put a value in, you're going to put an xy point into this equation to give you a new y value. And then you're going to increase x by the step. You're going to use this new y value, and you're going to put them into the same equation. You'll see in the example. So here's Euler's method more formally. So to get the next y value, you take the current y value plus the step size times the derivative evaluated at the current x and y. Let's see how that works. Okay, so we're going to let y prime, the derivative, equal sine x cosine y, and we're given the initial condition y of 0 equals 0. And we're going to use Euler's method with a step size of 0.1 to approximate y of 0.5. Okay, so what does all this mean? Well, oftentimes, first of all, it's easier to organize it on a table. Euler's method does get tedious and there's a lot to keep track of, even when you do use the calculator. And we're gonna use the calculator kind of a long way, and then I'm going to show you a shortcut. But even with the shortcut, it's nice to keep everything organized on the table. And so what this means, we're given the initial condition y of 0 equals 0. So our initial condition, we're starting off when x is 0, y is 0, and that's our initial condition. So I'm going to let n equal 0 for that. So this right here is giving me these two values. Now, we want to use the step size of 0.1 to get up to x equals 0.5. So that means my x values are going to increase by 0.1 each time until I get to a value of 0.5. So my step is really like my delta x, what I'm changing by each time. And so I'm going to do this 1, 2, 3, 4, 5 times to get there. So for this particular problem, my next value of y will be my current value of y plus h, which in this case is 0.1, times the derivative, which is the sine of the current x value times cosine of the current y value. This is my equation I'm going to work out each step. These numbers will change each time, but it's the same basic equation. This is the iterative process. So for the first time, right now in this first line, the value of n is 0. So that means n plus 1 is 1. This is going to give me the value for y1, which is the value of y sub 0, which actually I'm just going to fill it in. Y sub 0 is 0 plus h times sine of the current x value times cosine of the current y value. And again, remember n is 0, so x sub 0 is 0, y sub 0 is 0. These are the x values, the x and the y values for this line. Now in this case, we don't need a calculator because sine of 0 is 0. That's going to zero out this whole term. That means we're going to have 0 again, which is kind of nice. Nice way to start. This is my new value of y, which will go right there. And now I'm going to do this whole process again, but this time using this value for x and this value for y. So y2, the next value for y, will be the current value of y plus 0.1 times sine of the current value of x times the current value of y. And when I work that out, I have a calculator right here. I'm just punching the numbers in. And I get 0.00998333417. And that's going to go right here. I'm just going to truncate it a bit. So this number is right here. Now, I am not going to, even though I truncated it when I wrote it, when I work this out, I'm going to use the entire value of the calculator. Calculator actually has more than it's showing me stored in its memory. So it's got even more than all of this. I'm going to go ahead and store that into a variable. I know you can't see my calculator right now. Next example I'm going to show you, we've done storing before. Store is right above the on key if you forgot. So while this number is on my screen, I hit store and alpha y, and it's stored into my y value. And so now for the next line, the next value for y is the current value for y. I'm just going to write y2 instead of that whole decimal, plus h, which is 0.1, times sine of the current x value, which is 0.2, times cosine of the current y value, which is y2. And when I go ahead and do that, y plus 0.1 sine of 0.2 times cosine of y, I get about 0.0298492.847. And again, my calculator has a lot more stored than I'm writing. So this value is now my next value for y. And I do it again. So before I do this, see if you can pause the video and try to get the last couple of values for y. See how that works out? And then unpause the video and you can follow along. All right, so y4 is y3 plus 0.1 times the sine of the current x value times cosine of the current y value, which is 0.3. That's about 0.059388. And that goes down here. And so this value is now this one. And I'm going to do it again. The next value of y is y4 plus 0.1, my step, times sine of the current x value times cosine of the current y value. And when I do this, I get 0.0982613. And I'm going to stop there. We don't have to go further because remember I wanted y of 0.5. When x is 0.5, I have the y value that I want. No need to go further. Don't do it. That's one of the biggest mistakes, is that students will go further than they need to, and We don't need to do the whole calculation one more time. We don't need to finish the last line. We now know that y of 0.5 is about 0.098266 using Euler's method. So it definitely is a little cumbersome, but that's the idea behind it. Okay, so let me show you how to use the calculator now. I'm going to talk through it and then we'll do an example. So it's actually really easy because you enter 2 lines on your calculator and then you just hit enter, 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 enter. So what we're going to do is we're going to take our initial value of x. We're actually going to back it off. We're going to go backwards. We're going to subtract a step size and store that into x. So it's not our initial value that goes into x. We're behind a step when we store it into x. We take our initial value and store it into y. And we'll be able to use the colon on the calculator to put all of this in one step. So our calculator now knows our initial value of x minus a step and our initial value for y. Then what we do on the same line, so we're going to use that colon again, we are now going to increase our x by a step value. That will actually get us to the initial value of x. And then this is Euler's method right here. The current value of y plus the step size times the derivative with the current value of x and y. It will calculate that and automatically store that into the new y value. And then we just run this step again. It's going to increase x for us, so we'll get the new x value. It's already got the new y value in. It recalculates Euler's method and puts that new value in for y, and it just does that over and over and over again, and it's wonderful. So we're going to take this example here, and I'll show you how to do it. Now, I don't have a way of doing a split screen on a recording, so I won't be able to do that. I'm just going to set this up, and then I'll show you the answer after we do the step. I'm going to set up my table, and in this case, my step is 0.2, and my derivative is the sine. We're going to do the current x value plus cosine of the current y value. So go ahead and write this table down, and you'll see how great this is. And there's Crash. He says hi. Took him a while to make his appearance, but there he is. We'll see if he meows again. So I'm going to just set things up. Oh, there he is again. My initial value for x is 0. My initial value for y is 1. 0, 1 goes right there. I'm going to increase x by 0.2 until I get to 0.8. So 0.2, 0.4, 0.6, 0.8. 1, 2, 3, 4. So we'll have to do this 4 times. And that's all I'm going to write, and then we're going to use a calculator. All right, so I'm going to go ahead and go to my calculator, and I'll be right back. Okay, so here I am at my calculator, and let's go ahead and try this out and see how this works. So remember what I had on the notes, what we're going to store first. So our initial value for this problem for x is 0, but we're going to decrease that by a step, which is 0.2, and I'm going to store, and store is this button above on, so I hit store, and I'm going to store that into x. Now don't hit enter, because in this same line, I also want to store the initial value into y, and so I have to hit a colon. Colon is right here above the period, but it is in green, I have to hit alpha colon. And then I'm going to take that initial value of y, which is 1, and store into alpha y. So that's my first line. So this is, if you read it, we got x minus h, store into x, plus initial value of y, store into y. I'm going to hit enter. Now, when I hit enter, it's actually just telling me the last thing it calculated, and the last thing it did was stored 1 into y, so that's why it's giving me a 1. It doesn't really tell us anything. The next line, though, it will. I am going to take the current x value and increase it by a step size, which is 0.2, and store that into x, and then colon, and then I'm going to type the formula for Euler's method, which is the current value of y plus the step times the derivative, which in this case is sine of the current value of x plus cosine of the current value of y. But I'm going to store that value into y. And then I hit enter. That's my first value for y. And I'm going to go ahead and record this in my table just so I can have it. I know you can't see what I'm doing, but I will show it back to you in just a second. And here's the cool part. To get the next value for y, I don't have to do anything else but hit enter again. And there's 1.237. And then I'll hit enter again. And I get 1.380. And I'm going to hit enter one more time and get 1.531. And now I'm done. I just sped that process up a whole lot. And before I go away from the calculator, I'm just going to go ahead and clear this, our old value, our old table that we filled out. Let's just look at that real quick. So my initial value for x was 0, but I'm going to back it up by a step and store that into x. And then I'm going to take my initial value for y and store that into y. My next line, I'm going to take x, increase it by a step, store that new value into x, and then Euler's method, which is the current value of y plus the step times sine of the current value of x times cosine of the current value of y. We're going to store that into y. There was our next value of y, and then there was the next one, there was the next one, and if you're looking at your old table, you'll see these same values pop up. And that whole thing that we just took a long time to do, we just did 2 problems in like just probably half the time. So calculator is going to be your friend when you do the last few problems of your homework, which is Euler's method. Okay, I'm going to go back to the table just one last time and close things up.